The main way we understand what may happen in the future with climate change is with climate computer models. Some say the models have been broadly reliable in their early predictions. Others say that the truth is the exact opposite, that they've always been wrong and they provide no value at all. Well, let's have a look. The world is largely now committed to a process of decarbonising its energy, which is a huge step. It'll take decades, there'll be various difficulties to overcome. So we want the evidence base for that programme of change to be absolutely solid, obviously. Hence this video. Now, in case you're not familiar with this channel, the aim is to look at the question critically and with an open mind. If you're keen that models should be shown to be junk because it would reinforce your worldview, or alternatively, you're keen to show that they are absolutely validated on the most extreme outlier doom-laden predictions, all of that's fine, but it's not the spirit of this exercise. All right, we're looking to answer how successful or reliable are the climate models. We can't begin to answer the question unless we first understand what climate models are and what it is that they're actually modelling. Climate is effectively the distribution of possible weather states. So for instance, a distribution curve like this for potential temperatures in a location based on historical observation. The majority of instances around the mean, tailing off to smaller numbers of instances in the extremes, the extreme hot and the extreme cold. People ask the obvious question about climate models. How can we predict the climate for the next year or even for 50 years from now if we can't even predict the weather accurately in, say, 5 days' time? And the answer is that the climate is about probability. And that's easier to predict than the next event. If I toss a coin, you can't tell with accuracy what the very next toss of the coin is going to be, heads or tails. But we can say with some confidence that if I toss the coin 100 times, then the result will tend to 50-50. The chance of a hurricane in one part of the world next week depends on the current state of the weather in that part of the world this week. But the likelihood of a range of such events in 50 years comes down to probability. In many ways, it's easier to quantify. So, what is a climate model? It's a computer model that calculates world scenarios based on what we know about how the world works. So, for instance, the physical laws of conservation. Energy is neither created nor destroyed, only converted into another form. Models are used all the time. Mostly we trust them without thinking. If you decide that all computer models are junk on principle, then you would never get in your car. You would certainly never drive over a bridge, and for God's sake, don't get into an aeroplane. All those things have been designed and finessed using models, none of which were perfect when they did so, but they were good enough to be useful for their function. Climate models are in a special category though, and for good reason. And that's because they have to deal with multiple levels of uncertainty. And that's a fact, regardless of how good they are. One uncertainty, of course, is that the model could be flawed. Climate models can reach 1 million lines of code, and it's as susceptible to bugs and errors as any other software. But then you have two other unavoidable levels of uncertainty. One is scenario uncertainty. So you want to know, what will the global temperatures be in 100 years' time, Mallen? And I will say, well, it depends. How much do you think the population's going to grow in that time? What percentage of the energy they consume is going to be generated by fossil fuels? In other words, what are the CO2 emissions? How much of the planet is deforested or has been reforested? All of that is going to make a substantial difference. And add to that a dozen other questions, because humans influence the processes in a number of ways. You have to generate different predictions for the different scenarios of what they're doing. The other area of uncertainty is what's called the initial condition uncertainty. The more accurate a picture you have of the starting environmental conditions for the beginning of your model run, the more useful the output's going to be. Some things we know quite well, other things less so. Such as the state of the deep oceans and the upper troposphere, where historical measurement is absent or unreliable compared to the measurements that we have for other features like surface temperature. Now you have to take all three of those uncertainties to get a sense of the total uncertainty in a forecast. And the fact that uncertainty exists in modelling the complex global climate is not in itself a failure of the models. It's an inevitable part of the process you have to deal with. Let's then talk about the next layer. What are we actually trying to model? You can divide the climate into different building blocks: the atmosphere, the ocean, land, ice. Build models of how each of those works based on physical properties, build a representation of how they interact with each other. You have to deal with the Earth's overall energy budget. Energy comes in from the sun. It's then either reflected by the surface or by clouds, or absorbed by the atmosphere or the surface of the Earth. Sensible heat and latent heat are associated with water evaporation and condensation. Infrared radiation is emitted from the Earth, with some escaping to space, while some is absorbed by the atmosphere and clouds, and some of that is re-emitted back to the surface. This is the energy system, and in the first instance, any climate model has to account for all of that energy, and the simplest ones focus on that process. If more energy is incoming than outgoing, which is the case at the moment, then all of the additional energy has to go somewhere. And the processes by which things move around can vary enormously. Evaporation and precipitation take seconds to minutes to take place, whereas water that falls onto ice sheets may remain there for hundreds of thousands of years. Carbon dioxide and water vapour are the principal greenhouse gases and key to understanding the energy budget, but they also flow throughout the entire system. Hence why you need comprehensive climate models that look at the whole system. And then there are things that affect the climate, what are referred to as climate forcings. So for instance, the small fluctuations in the sun over a solar cycle, or the Earth's orbit and wobble on its axis that follows a cycle over thousands of years. Those all make a difference. You can't build in the ones that you can't predict, like volcanoes or meteor strikes, but the climate model has to build in those cyclical and the predictable climate forcings. And then you have to add in the existence of feedbacks. So for instance, if warming melts sea ice, the highly reflective ice is replaced by darker heat-absorbing water, and that leads to more warming than you would have got so long as the ice was still there. So that's what the climate models aim to represent. Each of the components has to obey the basic physics and chemical laws of the world, the conservation of mass and momentum and gravity, and the laws of thermodynamics, and so on and so on. Most of the physical science behind climate models is based on laws that we've known for hundreds of years. None of it has been made up on the back of an envelope. Okay, then the model has to take all of those laws and apply them to the globe. The Earth is split into a grid, and the model has to deal with 3 dimensions. How things flow across the surface, of course, but also up into the atmosphere and down into the oceans. How the water rises or sinks and moves in currents across the world. All of that has to be modelled. The vertical movement of air in a thunderstorm. So many different phenomena. You can see why this ends up in something like 1 million lines of code. And the amount of computing power you have to bring to running one of these models has become pretty immense, requiring the biggest supercomputers. The model has to take the physical state of the climate in each grid square at any time, figure out the processes and the physical laws that will change the quantities over a given time interval to then arrive at a new state. The physical laws are the constraints that the model won't allow to be violated. Whatever else happens, you can't go running around creating or destroying mass or energy or anything like that. But there are some aspects that can't be exactly modelled because they happen on too small a scale and in too chaotic a manner. So representing clouds in large-scale models isn't really possible. You have to approximate them. Building these elements in is referred to as parameterization. And it's a practical necessity and can be done with skill, but it's nevertheless a target for criticism because some suggest that it is an aspect of the modelling that deviates from the scientific method. We'll come back to that. So we've covered a lot of details just to get a sense of the nature of this thing. And it's important because the mistake people make is in thinking that a climate model is just supposed to be a window into the future. It should tell you for certain what will happen. But it tells us instead the probabilities of what will happen if certain things change to a set degree. All right, let's get to the meat. How have they performed? We've seen some of the real-time data since the earliest models were produced, so how did they compare? I suppose the first point is an obvious one. All of them projected that there would be ongoing warming, and in that they have been correct. Some skeptics, after all, predicted that within a couple of years there would be a new decline in temperatures, and that didn't happen. In the 1 in 3 random selection between cooling, staying the same, or warming, they were all on the right side. Now, obviously, it's not enough on its own. One of the first projections on future climate came from John Sawyer in 1972. This was obviously at the time when we'd seen a period of cooling from the 1940s to the 1970s. So nothing observed to date suggested the trend that he then outlined. He suggested that the world would warm by 0.6 degrees Celsius by the year 2000, based on an assumption of atmospheric CO2 rising by 25%. The key variable is always what is the climate sensitivity figure of how much warming a doubling of CO2 would produce, which remains debated and uncertain to the present day. He put it at 2.4 C, not too far off the 3 C used by most of the IPCC today. The warming prediction was close. The observed warming by 2000 was between 0.51 C and 0.56. But his assumption about CO2 concentrations were overestimated. So it's not as though he'd come up with the exact scenario to predict the exact result. He got the right result, but not necessarily for the right reason. This wasn't based on a computer model, of course, the like of which we're dealing with today. In 1975, Professor Wally Brooker used an energy balance model to estimate temperatures. This was close to observation for a couple of decades, where his assumptions about CO2 levels matched those that were recorded. But in recent decades, his assumptions had been that CO2 would increase a lot faster, so his model warmed faster as well. It's worth noting that Brooker's simple model can be an illustration of how the understanding of complexity makes a difference. Brooker only accounted for the impact of CO2. He didn't take account of other greenhouse gases. What we now know is that the warming impact from methane, nitrous oxide and the like has been largely cancelled out by the cooling impact of aerosols since 1970. So the emission didn't make much difference to his model. And that's how a model can look right, but for the wrong reasons. Which becomes important if things change and one of the factors stops being effective and the effect they were shielding suddenly becomes visible, which is why we still need to know the complexity. We need to know what's really happening under the hood, not just the short-term outcomes. In 1981, James Hansen et al. Published a paper that, again, used a simple energy balance model, but also added an allowance for ocean heat absorption. They produced different scenarios with varying future emissions and climate sensitivity. This graph shows a fast growth scenario, the black line, where CO2 is lower. The former was higher than actual emissions, but it was combined with a lower climate sensitivity of 2.8 degrees C, so it wasn't too far off the observed values. So look, if you're being tribal about it, you can argue about whether it was right or wrong, and you can take it either way. The line he drew nearly matched observations, so you can take that as a win. The line he drew was based on incorrect assumptions, so the fact it correlates with observations is a pure fluke. You can take that as a lose. You can do that if you want. The truth is that they did several scenarios because they were showing how different factors, the climate sensitivity, the rates of emissions, might impact the degree of rising temperatures. This was early days. So let's jump forward. It was 1988 by the time the first version of what you might recognise as an emerging modern climate model came out, and that was Hansen et al. Again. That model divided the world into a grid, as we've discussed. It included aerosols, various greenhouse gases, and basic cloud representations. And they put forward 3 different scenarios. Scenario A had exponential growth in emissions. Scenario B assumed a gradual slowdown in emissions, but growths of other greenhouse gases, some of which were actually banned under the Montreal Protocol. And Scenario C was more steeply declining emissions. Scenario B is the one that should have been accurate on the basis of the assumptions, given the fact it was very close to its estimation of CO2 as it was at the 2000 mark. But the fact it used a climate sensitivity of 4.2 C, which is on the high end of the range considered today, meant that to 2016 it was approximately 30% higher than has been observed. Whether you consider that to be a good first effort or a calamitous failure is up to you. Nobody was really thinking in those terms as the paper was being drawn up. But it was from this point onwards that the whole topic began to get more and more political. Because, well, for one thing, Hansen was showing graphs and arguing for radical changes in policy. And so it began. The IPCC first assessment report in 1990 used a simple energy balance illustration, but look, we've done those, so let's jump ahead to the 1995 IPCC assessment report, where they used a more sophisticated approach, particularly in how it factored in the impact of aerosols. Their mid-range scenario got the future CO2 emissions broadly right and came out with a projection that was lower than observations, suggesting 28% lower rates of warming up to 2016. This is possibly because they used a lower climate sensitivity of 2.5 degrees C. The 2001 IPCC assessment report, the scenario it used that matched the actual emissions outcomes, used a climate sensitivity of 2.8 degrees C and came out at about 14% lower than observations. If you've been persuaded that climate models have always been over-predicting warming, some of those should be surprising, I would expect. I mean, to be fair, they were to me. The 2007 assessment report was beginning to get more sophisticated in the broad range of factors that it included. Its A1B scenario, which is the one whose assumption of emissions matched what happened, shows warming 8% higher than observations, which is pretty close. The 2013 report is too close to the present to really judge, but in its performance to date it has been running hotter than its predecessors, around 16% above observations. It brought in the RCP scenarios, which we'll come back to later. Now, if you stop there, you conclude that, by and large, all these models have been broadly in the ballpark of what happened. Certainly no specific ongoing bias to be massively warmer than reality. And that's all very well, but although it's the most important headline measure, surface level temperatures, it's not the only measure. As you recall, the models are seeking to understand the temperatures higher in the atmosphere as well as at the surface, what's happening in the oceans, how fast the ice is melting, and all of those things as well. If you're looking at the overall picture, there seem to be 2 areas out of many others that seem to be the biggest points of failure. First, the surface temperatures may be close to observation, but if you go higher, the mid to upper troposphere, the models predict more warming than observations currently report. Second, if you look at the rate of ice melt, the model predictions have clearly missed some key component, because observed melting is a lot faster than any of the model scenarios. The grown-up scientific way to deal with this is to identify those areas as ones where there are issues, to use the anomalies to try to point to a trail of evidence where we can identify the errors, find ways to improve the models, and hence improve our understanding of how the world works, which by and large is what the scientists are trying to do. The political nature of the discussion means it's not what anyone else is doing, obviously. The skeptics jump on the first of those 2 phenomena to claim that the models are hopelessly wrong, and the catastrophists jump on the second of the phenomena to claim that we pass some terrible tipping point, and this means the whole system is following at least the worst case scenario and possibly even worse than that, in spite of evidence to the contrary. So, for instance, when I first started looking for the key critiques of the models and their performance, one of the earliest and most familiar ones was this graph, produced by John Christie. Here's another version with the different model runs shown rather than just the average. Why is this graph so different to the ones that we've been looking at? It's taking in that mid to upper troposphere temperature, so specifically picking out the area where we know there's an aberration. Well, fair enough, it's a real aberration, but there's nothing on the graph or how it's presented that puts it into that context. Second, there's no uncertainty range on any of the measures. Third, it averages together satellite datasets, hiding the fact that they are not in close agreement. That shouldn't be a surprise, by the way, that latter one. Satellite measurement is pretty new. Measuring the upper atmosphere is harder to do than the surface. If you hate computer modelling, you should probably hate satellite measurement, because transforming the signals that satellites get into a temperature reading depends upon a computer model. Now, of course, there are people who only hate computer models when they show the data they don't like, and yet they love the ones that show the data they do like. Christie's graph also ignores other measures that show greater upper atmosphere warming than the satellites do. Some climate scientists also said that the data wasn't properly aligned. It had been done in a way to exaggerate the difference. The explanation of how that worked was rather technical and detailed for a video like this, but even without that aspect, you get the sense that this isn't a graph produced to illuminate rather than to confuse. And that's unfortunate, because the issue is a real one. And, we could have a grown-up discussion about it. This paper by Santo et al. In 2017 looked at the causes of differences between model and satellite tropospheric warming rates and concluded this. We conclude that model overestimation of tropospheric warming in the early 21st century is partly due to systematic deficiencies in some of the post-2000 external forcings used in the model simulations. Now, if you're curious, then you need to think, well, we know the energy can't simply disappear. So if the models think it should be going into the upper troposphere and it isn't, then where is it ending up and to what effect? So let's ignore the easily debunked misleading graph makers. Where are the more solid critiques? One is the argument by skeptics Soon, Connolly and Connolly that the IPCC has chosen a model for the sun's input that understates the variability that they argue that it brings. Their argument is given low credence by the scientific community, and the debate behind all of that is kind of out of scope for this video. But the central proposition, of course, is that the models are only robust when they've incorporated all the correct factors. One of the more capable critics of climate models is Judith Curry, who doesn't indulge in the rhetoric of the models have always been wrong, but does make some telling critiques. One, she says, is that the models are too much tuned to fit the recent past, in a way that makes them appear right, but without guarantee then to their future predictive effectiveness. Concerns about evaluating climate models have been raised in the context of model calibration tuning practices. And she quotes an article in the journal Science, which said this: whether climate scientists like to admit it or not, nearly every model has been calibrated precisely to the 20th century climate records. Otherwise, it would have ended up in the trash. It's fair to say all models have tuned it, says Isaac Held, a scientist at the Geophysical Fluid Dynamics Laboratory. And she concludes, we are now in a situation whereby matching the 20th century historic temperatures is no longer a good metric for determining which models are good or bad. She also argues that the IPCC significantly overstates climate sensitivity and points to the fact that after decades of development, the range between 1.5 and 4.5 degrees C, which they use, is still very broad. She argues it should be below 2. And that this matters because of the weight being placed on the models to inform public policy, which of course is the point. But the most trenchant criticisms, it seems to me, come down to focus on the scenarios. Now, I mentioned that the 2013 IPCC report brought in the RCP scenarios. These are absolutely key because, as we mentioned, you can't know what humans are going to do in the future. You have to factor that into your projections. It's reasonable to argue that when it comes to the public discussion of the results of computer models, there has been serious scenario abuse. The RCP 8.5 scenario was mistakenly referred to as business as usual, a description that then stuck and has led to its overuse in any public discussion in the output of climate models. It presumed a major increase in human population beyond what we've seen. It presumed major deforestation, and more to the point, it presumed a massive increase in the use of coal, which is not even remotely on the cards. Now, on the one hand, This is a so what. Other scenarios are available. And if it turns out the most optimistic one, scenario RCP 2.6, is the one that actually matches our emissions profile, and then the predictions for that scenario match what actually happens, that's a win for the modelling. But which scenario output is driving public policy? Which scenario is reflected in the headlines, which are being relayed to anxious and scared children? At that point, you have to say the real challenge to the computer models isn't that they're always wrong, isn't that the internal workings are somehow badly done. That's not been the case to the degree, certainly not to which it's alleged. It comes down to the uncertainties that are undercommunicated, probably because people are shadowboxing the critics. And it comes down to the results that are shaping action. Because although more correct ones may turn out after the event to have come from the model, those are not the ones driving policy. We should judge it by the ones that are. And for me, this is why the models are inherently useful and yet are being profoundly perverted from their task. We compare models and observations, ideally to learn something about the real world, not just to score points in some spiralling debate. Understanding that when you program in everything we know about the physical world, we nevertheless get some results that seem to differ from what we would expect, that is incredibly useful information in tracking down those differences, and therefore learning about the things about how the world works that we didn't previously know. That's what the various scientific graphs and reports are designed to do. The graphs of people like John Christie are there to make a single argument that the models are wrong and therefore should be discounted entirely. I know lots of people have taken that message to heart, but ask any risk manager whether what you don't know is a risk or an asset. So look, here's my conclusion based on what I've seen to date. Are the climate models always wrong and therefore zero value? No, certainly not. And the idea that they're expected to be perfect and complete representations of reality is kind of to misunderstand what they're for. Are the models currently good enough? No, clearly not. Upper troposphere temperatures are wrong, we need to know why. The rate of ice melt isn't explained. We need to know why. We still can't work out climate sensitivity. Well, we need to do better. But you know what? People are working on it. Are computer models fit for purpose? Well, that depends on the purpose. Right now, the abuse of worst-case unlikely scenarios to put the most extreme predictions in front of people, that is a huge failure that could undermine the integrity of the whole operation. If I was asked the same questions and the only version of a computer model output that existed was that based on RCP 8.5, then the answer would mostly be different. Yes, always wrong. Yes, zero value. Only the no, not good enough would stay the same. It's not to say you can't benefit from an extreme scenario to understand how the climate might respond, to give you some sense of what thresholds exist and all of that. Yeah, there is some value there. But if you're only going to default to focusing on the worst case scenarios, then you should lock that one away and introduce a worst case scenario that is nevertheless at least reasonable. The climate models are useful tools in helping us to understand the world better, to highlight the things that we don't yet know. They're not the settled science of the consensus that should be taken as justifying every policy initiative that somebody wants to push forward. And once again, they can be seriously misused. But you know, in all the research I've done for this video, I've seen climate scientists talking openly and frankly about the problems and issues, seeking ways to improve the models, being rational about what the models do and don't mean. Not hiding flaws, not covering anything up, not biasing results only one way. And there's no version of this discussion that wouldn't benefit if all the participants couldn't proceed in the same spirit. I know, crazy.